Very warm welcome to our webinar today. The topic is on system reliability and maintenance, key success factors for your business. This webinar is organized by the Center for Advances in Reliability and Safety, in short, CARES. I'm Dennis Zhang, Program Manager of CARES, and I'm delighted to be your MC this morning. Let me introduce to our local speakers, Engineer Wilson Kwok. He is from the Head of Technical Service, Hong Kong Electric. His topic for us today is application of AI in the reliability and security of power grids. Over to you, Wilson.
Okay, thank you. Thank you very much. Would you please go to my PowerPoint presentation? So before the PowerPoint is on, let me give you some background information about Hong Kong Electric. Hong Kong Electric is according to our research, is the oldest power company in the world. Not in Hong Kong, but in the world. The reason is that we was established in 1889. And we haven't changed our name since then. But in the world, there are many power companies that changed their name. So that's why we are the oldest one now in the world. Hong Kong has two power companies. We are Hong Kong Electric, and the other one is CLP Power. Hong Kong Electric has maintained a very reliable power supply since 1997. We achieved 99.999% since 1997. And 2 years ago, we even achieved 99.9999%. And for last year, 2020, we break the record, but it is not audited yet. We will disclose this later, and we even achieve a much better reliability. So yes, 69, 4 line after the decimal. So in other words, it means that for those unplanned outage, each customer has less than 1 minute electricity loss in a year on average. So this is really a world-class supply reliability. The reason behind is that we moved into what we call smart grid about 25 or 30 years ago. We start to automate our system. We start to install sensors, a lot of equipment in our substations, so that our engineers can monitor the system in the control center, and in case there's any problem, they can restore the network or restore the supply in a very short time. So, but nowadays, many people talk about smart grid. So, in fact, what is smart grid? Smart grid means the grid is smart. The grid has intelligence that it can operate itself, depending on various conditions. So on this slide, this is an analogy between a human body and a smart city or a smart grid. So why people is intelligent or smart? Because we have brain that make the decision based on the information from our sensors. And how the sensors and information bring back to the brain, it depends on our body. There are many neural networks, there are blood vessels that bring everything back to our brain. So in a city, it means that we have to deploy a lot of sensors in the city. So what are the sensors for the city? We have like CCTV cameras, we have environmental sensors that sense the temperature, the pollution conditions, we have humidity, and so on. So from these sensors, how this information bring back to the control center? It depends on a very sophisticated communication infrastructure. So nowadays we have 5G, and we have a lot of other kind of IoT solutions like NB-IoT, 6Box, or LoRa network. So these are all the communication infrastructure that facilitates the smart city deployment in the city. So what we need is, based on this information, based on this communication infrastructure, it brings back to the brain, what we call the dashboard or the city control center of a city to control or to monitor the whole city. So in a smart grid, it is similar. We have to deploy a lot of sensors in our grid, And we have to deploy a sophisticated communication infrastructure inside our company to bring back all the information back to our control center. And we have just like 2 or 3 engineers sitting back in the control center, look after the system, and let the system run and run, depending on different scenarios. So here are the key elements of a smart city or a smart grid. So we have the brain, what I've mentioned earlier. We have the sensors. So sensors have a lot of kind. From here, I mentioned about the CCTV images. It also can be some acoustic sound from the transformers. It can be also the voltage, current, and phasor of the power grid conditions. So the body, as I mentioned earlier, we have to deploy a very comprehensive and sophisticated infrastructure to support these sensors and bring it back to the control center. So later on, I will share 3 use cases with all of you. Well, I believe that I'm the only industrial representative in these areas, and when we talk about very detailed technologies, I will leave it to Dr. Boo and other professors and doctors. So what our engineers can do is how to leverage the latest technologies and make best use of it and apply it to our power grid, to make it smart, to make it more resilient, make it more reliable. So from here, we have, what we are thinking about is, now, we have a lot of substation, unmanned substation. We have more than 4,000 substations unmanned. We have already deployed a lot of sensors like current, voltage, temperature, etc. But there are some cases and there are some pain points that we cannot detect, or we need to deploy someone to site to report to us that there are some abnormality. For example, there are some hotspots on this is a fuse panel, how we distribute the energy to our customers. So if, as time goes on, there are some loose connection in the fuse panel because of tear and wear, because of other reasons. And if the connection is not good by the law of physics, the resistance will develop. And when currents flow through, it will become a hotspot. And if the heat increases to a particular area, threshold, it may turn into a fire or burn the fuse panel, and it will affect the power supply to our customers. But, developing a hotspot is not 1 second or 2 second event. It may take like half a year. That means that if we can deploy an eye by people full-time monitoring the hotspot, we can see the trend that the hotspot is developing. So what we are going to do is to deploy IR cameras to monitor the panel and see if there is any potential hotspot developing. And in case if there's any, we can do it before it develops into a permanent fault. And it can further improve our supply reliability. So this is one of the use cases that we are doing now. Another one is Hong Kong has a lot of typhoon and a lot of rainfall in the summer. And because our equipment are housed inside a substation provided by the building owner, occasionally, because as time goes on, the floor ceiling deteriorates and water may leak from the ceiling. So in the past, we need to deploy our engineers to site to see if there is any problem with the ceiling, any water dripping down to our apparatus, or any flooding in the substations. But when we think of if we can deploy CCTV, we can know whether there are some water dripping from the ceiling. But the substation is very big. We cannot deploy a lot of CCTV. So maybe I will ask you a question. If you were at your home, how can you know that some water is dripping from the ceiling? Not from the eye. You can hear it, right? When something drips onto a metal, da, 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 right? So if we can deploy sensors together with CCTV, when this information correlated together, we know that there is a potential water dripping on our apparatus. So this is also the area that we are looking into. And when there are some buildings close to the coastline, according to our past experience, some water may rush in, flood in into our substation. We are also looking into a solution that using CCTV, monitor the level of the water, and as time goes on, we have the times, right? And then the change of the depth of the water flooding against the time, we can know the rate of flooding. So if there is a wide area flooding in Hong Kong, and we have more than 4,000 substations, we cannot handle all substations at the same time. So depending on this information, we can predict the rate of flooding, and we will put more focus on the high rate one, and put that focus on the lower rate one. So this can prioritize our operations of our engineers. So this is also the area that we're looking into. So this is a very high-level system architecture of a substation monitoring. So you can see that there is a monitoring center. This is the brain of our substation monitoring. And there are many sensors in our substation, like the CCTV, like the voltage, current, temperature, flooding sensors. And how we bring this back to our center is relying on our in-house communication network. So this is the way we build our smart grid in Hong Kong Electric. So another area we're looking into is based on some our historical information as well as some weather information. So the next project we are looking into is we call the intelligent walk-while regulations. So in layman terms, I can tell you that usually we only use the resistive power, but because of many other reasons, there are some other reactive power in our power system. So reactive power is a kind of a loss of energy, and it will decrease our efficiency and the power utilization. So we have to find a way to improve the voltage and to decrease, reduce the reactive power. So in the past, we will, based on the seasonal information and the past load information, to kind of predict and to adjust our system in order to reduce the reactive power. But nowadays, we are now looking into some kind of RNN, some neural network, to collect information from the environment, for example, the weather information, and also the existing load conditions, and how to predict the increasing in load and also the increasing in the reactive power. So this is the system block diagram that we have two main systems. We call the EMS, Energy Management System, and the DMS, Distribution Management System, and a lot of sensors in our substations. And this is a closed-loop control with the customer's substation as a feedback. So the next stage is we are starting to use a recurrent neural network to enhance the prediction of the load trend, so that we can derive the capacity control direction in order to reduce the reactive power. So I'm a layman in this area. Probably Dr. Bu is an expert in this area. Later on, he will elaborate more about this area. We can, based on some historical information, we encode it and then put it to the neural network, and we can decode the prediction based on this historical information and some other external information. So this is some proof of concept that we have done in last year. As you can see from this graph, the blue and the red one are the 5-minute and 20-minute moving average of the customer load. And because we deploy the RNN, we can early detect the increasing in the customer loads and the capacity load. And we can early catch up the green curve to start to jump in at 6:15 in the morning. And it can recorrect and catch up the load curve at 7 o'clock. Without RNN, we cannot do it, and we can only do it at 7 p.m. when the load increases to a certain level. And then we will lag behind, and we will waste some power in this situation. So that means that AI or RNN can probably not only improve the reliability and also improve our efficiency of the power network. So the last topic that I'm going to share with you is that as a power company, we have many power cables laid underground. And actually, we have low sensors. I mean, low online sensors that online monitoring all these cables. And these cables are very important in the power delivery to our end customers. In case any cable fail, it means that not only one, but a group of customers may lose powers. So we start to think of way to improve or to predict when a cable will fail. On this slides, we give you, well, as I mentioned earlier, we were established more than 100 years ago. A lot of cables are laid many years ago. And the cables nowadays buried underground may age over like 40 years, and they are reaching their end of service life. So we have different kind of cables, and different kind of cables have different kind of characteristics. So how can we tackle this? We found that a particular vintage of the cables, we call XLP cables, manufactured in the 80s, we found that there are some potential fault because of the immature technology at the time of manufacturing in 1980s. We found that this insulation has some impurities on voids inside these plastics. And as time goes on, and if there is water around, it may develop into what we call a water tree. And I believe that, you know, water is a pretty good conductor. And if it develops into water tree, it will degrade the insulation. And from time to time, and time goes on, it may become a weak point in the insulation. And partial discharge may happen in this area. And if it happens, it means the cable will be damaged and burnt. So we have to find ways to predict when a cable will become faulty. So in the past, we have conducted a lot of tests and collect a lot of test data, mainly based on two areas. We call the partial discharge mapping and the very low frequency tangent delta measurements. These two tests have their unique functions, and they cannot replace the others. The partial discharge can locate the weak components in the cables or in any apparatus. But for very low frequency, it cannot exactly pinpoint the fault location, but it can indicate the overall performance of the cables. So with these two tests joined together, it can supplement each other and provide very useful information to us. So in the past, we have many information offline in our system. And last year, we start to share this information with CARES. And we believe that based on this abundant information and data, we can correlate them together. And based on the past history, because we have the information when the cable will become faulty, we believe that based on the past information and the data, with some big data analysis, we can predict the faulty cable component because it becomes faulty. So this is the area or the direction we are looking into now. We are working with CARE Center to do some artificial intelligence methodologies to process and analysis the data from two systems, but this is offline, from the VLF test as well as the online PD test, so that we can pinpoint the damaged cable, the cable that has potential fault, becomes damaged. The reason is that if the cables become damaged or faulty, we take a lot of time to dig it out from the ground. We need to seek approval from different government officials. We need to seek consensus from the district officer, from the public, before we can arrange the road work. So if we can predict the fault cables or faulty components, that means we can do it in advance and to prevent a power interruption to our valuable customers. So this is the area, the three areas that we are looking into. And this concludes my presentation today. Thank you.
Thank you. Thank you, Wilson. It's very nice to have industrial side of sharing your experience, and this echo well with the first presentation on reliability prediction of there's many environmental factors that we have to consider. So thank you again, Wilson, and to the audience, and may I also invite you to leave your questions using the QR code as shown on the screen. We will answer your questions at the end of the fourth presentation by Dr. C.G. Boo. So let's move on. Dr. C.G. Boo is the Associate Professor of the Hong Kong Polytechnic University, and he will present us today his topic on data-driven technique in enhancing reliability and security of power networks. Dr. Boo, please.
Yeah, thank the organizer for this special opportunity, and also thank everyone for tuning in. So I think it's approaching lunchtime, so I try to finish soon. The topic today I would like to share with you is the data-driven techniques in enhancing reliability and security of power networks. So before I start, I just want to make an acknowledgement to the main contributor in my research team, Dr. Chi Wang. And actually, I'm not a data scientist. I'm just a power system engineer or power system operator. So later, if any question related to the data analytics, I will try my best to answer. If I can't, I will actually direct your questions to the right person in my team. So without further ado, let's get it started. Okay, so the agenda for my talk actually is listed on the left-hand side. So firstly, I will talk about some background for the AI and big data technology, and then I will move on to three typical applications. So I think the previous speakers had talked a lot about the theory of the machine learning, deep learning in improving the reliability, as well as the predictive maintenance. So here come some very good examples in power industry. So I would like to share with you. So firstly, I would like to talk about some, the so-called 4D transformation in power industry. So the 4D transformation are firstly decarbonization, and then digitization, decentralization, and deregulation. So this 4D transformation actually happened in all levels of the power industry. It means in all the entities. So I take the decarbonization as one example. So the decarbonization means we would like to replace the conventional thermal or fossil fuel generation with some renewable energy, such as wind, solar, or water. So actually, it can happen to the big, the power generation plant, or it can happen to the so-called prosumer. So we can install, the PV panel on the rooftop, right? Then we can actually feed the electricity back to the grid. So with this 4D transformation target or initiative, there are quite many enabling technologies. So I've listed some of the technologies here. Most of them actually are from the Industry 4.0. So the highlight one is the AI, which I would like to focus on today. Here it presents some, the evolution of the AI. I wouldn't go into details, but like many new technologies, AI actually experienced ups and downs in the past few decades. But since I think 2006, especially after 2010, the machine learning and the deep learning actually become very hot topics, and they have been applied to to the power industry. So we have seen quite many data applications in power systems. For example, like the renewable energy forecasting, demand forecasting, as engineer Koch just mentioned. And also, there are some other applications, for example, like situation awareness, as well as some predictive maintenance. I'm gonna share with you in a moment. So first case I would like to share with you is the application of the deep learning or the big data technology in improving the reliability of the power system. So in order to improve the reliability of a power system, firstly we would like to improve the reliability of the power equipment. So there are some challenges there, for the modern power grid. So we have seen more and more integration of the power electronics components to the power grid. So it has sort of changed the characteristic of the equipment. So the equipment become probably more sensitive to the external conditions, more vulnerable, invisible. So it actually poses a challenge to us in terms of the maintenance. But with the development of the maintenance theory and technology, actually it facilitates our the reliability improvement. So here I just want to brief the development history of the maintenance. So as has already been actually mentioned by previous professor, so the first stage actually is related to the so-called corrective maintenance. So we only carry out the maintenance after the breakdown of the equipment. So of course it is quite costly because it might lead to even more severe damage to the power equipment. So the second stage is related to the preventive maintenance, which means we schedule the repair or the replacement periodically. So this type of maintenance actually sometimes has underestimation or sometimes has the overestimation problems. So underestimation will lead to probably potential damage to the power equipment. The overestimation will lead to probably overspend or the cost and the work pressure to the personnel. So these two maintenance is not quite ideal in terms of the cost as well as the reliability wise. So in early this century, the U.S. government introduced a policy or implement a policy called the condition-based monitoring plus, which represents an effort to shift this unscheduled or pre-scheduled maintenance to the predictive or condition-based monitoring maintenance. So the predictive maintenance actually is a typical example for the condition-based maintenance. So this type of maintenance actually is based on the health management. It's a data-driven method. So with the introduction of a predictive maintenance, we can improve the reliability of the power equipment and power system to a highest extent and in a cost-effective manner. So to utilize or to implement the predictive maintenance, one of the biggest challenge here is the lack of data, is data deficiency. Normally, when we purchase some power equipment or when we operate the equipment, obviously we hope the equipment can work forever. We don't expect there are many problems. So it is normal case, but it also gives us trouble because there's a lack of the failure data and the failure cases. So that's one of the challenge we face. And the other one actually is for most of the data-driven method, especially for deep learning, it require data consuming or demanding. It requires a lot of data actually to predict an accurate result. So this kind of two contradiction we encounter actually gives us some challenge. So the solution we propose in our study is a fusion methodology, which combines the model-based and data-driven approaches. So the model-based the method, which is so-called the proactive maintenance here, or sometimes later we call it a sample generator. It is basically a physical model derived from the theory of a probability and the stochastic process, which describes the stochastic behavior of the failure time of power equipment under the degradation and failure mechanism. So this is one side. On the other side, we have the predictive maintenance, and we also call it a maintenance predictor. So this one actually is formulated by the deep learning, specifically the LSTM and RNN techniques. So the RNN, as Engineer Kok just mentioned, it is very good at dealing with the time series. So it is equipped with ability of memorizing the dependency between adjacent time steps. However, it also has a shortcoming in memorizing long-term dependency. So that's why it's a variant, LSTM, long short-term memory, RNN is used in this study. So with these two combined, so we can solve the data deficiency problem. So if we look at the flow chart or the diagram on the left, bottom corner, so after we determine which power equipment to analyze, we can determine the failure parameter, and then we can use the sample generator to firstly establish the physics model, and then we can generate data by using the Monte Carlo simulation, and then this simulation data can be used to train the model, to test the model, and also to validate the model. So and then later on, with the field data coming, we can actually we can predict the future the maintenance timing. So before I go into the details, I just want to brief the background of this project. So this project is a collaboration with the high-speed train China, high-speed railway China. So as you might know, in the past couple of decades, the high-speed train has experienced a booming development in China. And a lot of new lines enter into service. On the other hand, the traction power supply system, we call it TPSS, actually is the most important part in the plays a very important role in this this high-speed train operation. It actually feeds the train. But it has a very intensive and persistent workload, which make the fault and the failure of the power equipment become inevitable. So under this condition, so one of the most remarkable characteristic for this TPSS is the the load of the the power supply of the high-speed train will always experience a frequent shocks. So this is a typical characteristic of this the load and the TPSS. So these shocks actually make a very harsh condition for the power equipment. It makes the power equipment not only prone to instantaneous failure, but also suffer from the accelerated degradation or aging problem. So that is why in this research we have modeled the physics of failure into two different categories. The first category is so-called hard failure. The hard failure actually considers the temporal as well as the spatial randomness of the shocks of the load. So if you can look at the diagram in the middle on the right hand side, so there's some arrow. You can see when the green arrow exceeds the threshold, which is the horizontal line, we call this one is like the so-called spatial kind of feature of this randomness, and it is described by the extreme shock model. It is like a probability model, and this model actually we assume it follow the normal distribution. And the other hard failure actually is when two consecutive shocks come together. It's too close. The timing is too close. Then it will actually bring a hard failure as well. And this physical failure actually is described by the homogeneous Poisson process in our study. So apart from this hard failure, we just mentioned there are some soft failure as well. So the soft failure actually has two subcategories as well. The first is the aging. It's a gradual aging. It's normal aging problem. The second one actually is the accelerated aging or degradation problem, which is caused by the shocks. So these two failure are described by one by the Poisson process, and the other one is by the gamma process, according to their characteristic. So by establishing this probability model, we can actually produce the data and form this sample generator. And then we come to the second part of this approach is the maintenance predictor. So if you can see the workflow, the chart on the right-hand side, so after we determine the failure parameter, and then we can actually establish the physics of failure model, and then we can do the Monte Carlo simulation to generate the simulation data and feed into the predictor to train the model, and then we can further tune the hyperparameter, and then further validate the predictive model, and then finally, if we have the field data, we can predict the maintenance timing. So we are using the STM technique in this predictive model training. So here are some results. So we try different optimizer, for example, like standard gradient descent, and some adaptive moment estimation method, and then we found the extension of the adaptive the moment estimation technique is the best, so we select because it has the smallest loss function. And also we trained the major hyperparameter, for example, like batch size and the epoch. So we just by the training, we can actually tune the hyperparameter. So and we also use the sample data as well as the field data to validate our training model, and we found out actually this training model is quite accurate, and the results are acceptable and satisfactory. So to sum up this case, so this is actually technically designed for the switchgear, but actually it can extend to other power equipment. And this is a combination of the model-based and the data-driven techniques, which has two major advantages. First one is it can solve the data deficient problem. The second one is it can provide the system operator or practitioner with in-depth understanding on the physics of failure, and they can actually comprehend this problem better. So this is the first application I would like to share with you. The second one, actually, probably I just cut it short because the theme of today's webinar is related to the reliability and maintenance. Actually, the second and third is related to the security of the power system. So the background or the context is, I just mentioned there are 4D transformation, right? So with the decarbonization, actually we have more and more renewable energy or sources connect to the grid. So it make the grid more actually dynamics more vulnerable, and there are more cases with instability or insecurity. So basically, there are quite many dynamics change for the system. So a typical or well-known case or incident is actually the London blackout happened in 2019, 2 years ago, which caused actually 1 gigawatt power supply interruption. So cannot compare with the Hong Kong Electric reliability. And also it affect almost over 1 million population because it's during the the rush hour in the afternoon. So the problem with this one actually is related to the loss of different generation on the transmission level, on the sub-transmission level, as well as the distribution level. So with the conventional dynamic security assessment tools, it fails in predicting the system insecurity. So that's the reason we would like to introduce this situation awareness tool to solve the problem. The situation awareness concept actually it was proposed by the U.S. The military in last century, 1980s, 1990s. So it is actually was introduced to the power system not quite long ago. So it is a tool to complement the dynamic security analysis. And another challenge we have here for the situation awareness is how to deal with the more and more complex, the communication and data corruptions. So here I list, 2 examples. The first one is the Ukraine blackout in back to the 2015, and this blackout actually is quite famous. Because it is probably the first time reported to be affected by or caused by the cybersecurity issue. The second example actually is the U.S. government implement a legislation to insulate the power equipment from the digital control in order to ensure the security of the power grid, which is issued in 2019. So these 2 examples actually can demonstrate the importance of dealing with the cybersecurity issue in the situation awareness. So by using the deep learning based situation awareness, we can actually sort of deal with the data corruption issue. So that is why we propose this enhance the situation awareness based on the random matrix and the deep learning. So the deep learning or the STM actually is used to predict the sequential data, and the random matrix actually is used as a pre-processor to implement the data cleansing, the feature selection, etc. So based on this random matrix theory and a single spectral theorem, we actually there's a proposed indicators called MSR. So this MSR can be used for the insecurity indication. However, due to this random matrix, it is kind of immune from data corruption. It makes this situation awareness tool not so sensitive, to the so-called anomaly of the system. So sometimes the case is when the anomaly is similar to data corruption, this situation awareness tool cannot differentiate these two. So that's why we propose a so-called GCSE indicator here to identify the genuine anomaly of the system. So here are some demonstrated results. We use the New England, New York system, benchmark system to test. The red point here actually is deployment of the PMU. So maybe later we will talk about the validation of the number of PMU. So, but now it's like it's kind of a distributed, deployed. So for this system, we applied the persistent line, break fault, and you can see on the left bottom corner. This is a plot of the MSR and the proposed GCSE, and both actually can detect there's an anomaly and a fault in the system. So based on the eigenvalue of the distribution of the eigenvalue of the random matrix, actually you can see the system cannot come back to the normal operational condition anymore after this persistent fault. So we also have some special design for the data corruption, like there's some cyber attack, some data delay or data dropout, and also we actually use different system fault or disturbance to test these techniques. So actually it resulting a quite good accuracy. So we also test the small disturbance cases. So this case actually for the MSR it didn't detect any insecurity because it is a small disturbance. But for the proposed GCSE, it can actually detect the genuine anomaly. But at the same time, it removes the impact of the data corruption, which is designed by us. And if you look at the left hand side, this bottom corner, there's also a validation on the performance of the techniques, based on different number of PMU deployed. So it can be seen here. Initially, we have 16 PMU deployed in this system, but we can reduce the number to probably 4 PMUs in the system. It can still produce a very accurate result. So the previous case, actually, we are detecting the anomaly in the system. So for this case, we would like to bring the situation awareness to a new level. So when situation awareness, this concept is proposed, actually there are 3 levels. The first level is called perception, second level is called comprehension, and third level is called projection. So projection means prediction. So for the benefit of system operator, from the perspective of system operator, there are 2 main factors we would like to know. The first one is where is the fault locator. The second one is what about the future status of the system after fault? It's going to be insecure, unstable, or it's going to be okay? So in this case, actually, we use the temporal as well as the spatial feature of the data to actually detect or predict the future status of the system as well as the location of the fault. So we're using the deep learning, the CN plus LSTM. CN is used to locate the fault, and LSTM is used to actually predict the future state of the power system. If you look at this flow chart, so after the training and the model, then there are two indicators. The first one is the locator. The second one is a predictor. And after that, the system operator will be alerted. So in a very short time, after fault, they can have a very fast post-fault action. For example, to clear fault, to have intertrip, to deload the generation, or have some line switching in order to mitigate the negative impact of the fault. So I'm not going into details to this techniques. So here are some results. So we are still using the same benchmark system, and we are deploy the PMU to each generator first. So we have 16 generators, so that's why we have 16 PMUs. And we found out actually the loss function for the locator actually is a bit challenging, to decrease. But ultimately, actually, we can have an accurate, result for the average. The prediction accuracy for the locator is around 95%, and for the predictor is around 98%. So it's quite effective. We also try to compare our algorithm with some existing deep learning or machine learning techniques. So we found that's the better solution. And also we look at some practical factor. For example, we try to actually to decrease number of PMU, and also we try to decrease the time period of data after the fault. So these two actually, one is kind of like a spatial feature, the other one is a temporal feature. So to decrease these two, both will contribute to the the less accuracy of the prediction. But we found out actually to achieve an acceptable level, it's better to have 11 PMU deployed in the system, and the minimum length of data should be 0.4 seconds. And also we look at different PMU deployment style. For example, we can have a centralized deployment. We can also have the distributed deployment. So both can actually can bring a very satisfactory result. Okay, so the last one actually we actually apply different fault. So it actually validate the performance of our proposed techniques. So to wrap up this technique, so based on this technique, we can predict the accurate location of the fault, and we can predict the future status of the system, and within a very short period of the time after fault. So even it is faster than the protection relay, so it gave the system operator more time and room to to implement more post-fault action to mitigate the impact of the fault. So I think for the interest of time, this is the end of my the talk. So thank you very much.
Thank you, Dr. Bu. It's quite a fascinating presentation because there's so many research areas that can be applied in predictive maintenance and in power systems. Right. So let's begin our second section of our Q&A. So let's see what we've got here for the questions. So the first question is to Wilson, and it's quite an interesting one. So have you ever encountered a situation in which that the data-driven maintenance schedule is different from the original maintenance schedule? I guess it's the preventive maintenance schedule. If so, how would you address the concern of the risk of delaying some of the maintenance work with lower priority according to the data-driven schedule?
Okay, thank you very much for these questions. And this is a very interesting question, whether the AI or the computer is right or our human brain is correct, right? So when we, as a power company, we usually do it in a more pragmatic approach. So we have our own maintenance schedules, and based on the AI or the condition-based or even the predictive maintenance, it will come with another kind of maintenance schedules. But we will usually not very aggressive at the very first time. For example, if we schedule it to do it every year, and somehow the system tells us that you can do it every 2 years. We may not do it every two years at the very first time. We do it pragmatically, progressively. For example, we may take an approach like 1.3 years or 1.5 years and see how it performs and how the system reacts. And if there are some buffer that we can further extend the maintenance schedule, then we will further extend it to like 1.7 and then eventually to 2 years. So this is the way that how we take the AI or the predictive maintenance information, the result, into our system operation.
Yeah, thank you for Wilson for his sharing on the risk-based approach for adopting AI in maintenance. So another question is also to Wilson is that given Hong Kong Electric have the sensors installed, real-time data from sensors and new network, how Hong Kong Electric estimate the forward-looking parameters such as the rest of the useful life, expected time, downtime, etc., and other predictive analytics by applying AI?
Right. The purpose of using the historical data on the online data, in the past, we based on the historical data to do a condition-based monitoring or to predict the remaining useful life. So we believe that as more sensors can be deployed online, we can collect more information. And based on this, as mentioned by Dr. Bu earlier, and also the doctor in University of Maryland, they also mentioned that based on this kind of information, we can work out a model to predict the remaining life of our equipment. And this is exactly the direction that Hong Kong Electric is looking forward to, having a predicted remaining useful life. For example, we have some power cables laying underground. Some are laid in a more a better environment. For example, there is no disturbance from other utilities. This is a private area, and as long as the cables and the load is not very high, for this situation, the cables can work even longer than 60 years because they are not overloaded, they are never disturbed by other factors, there's no water around the areas. So this information from the past, we can only have the historical information. But if we have the sensor, we can know the and also the input from the weather, the Hong Kong Observatory, we can know the weather conditions. If we have the sensor, we can also know the humidity. If we have the temperature, we also know the loading of the cables. With all kinds of this information and bring it back all together, we believe that we can predict the useful life, that it may be longer than 60 years. On the other hand, if some cables are laid in very adverse environment, many people dig out the areas, may disturb our joint, and may also, in this case, may affect the useful life of the cables. We believe that from the operational information, we will know that the cable's performance will degrade. And based on also the history that the cables is not in a very congested area, we can also increase the risk factor of these cables. And in that case, we will reduce the useful life of this cable, and we can plan ahead to replace the particular cable sections to avoid a permanent fault develop.
Thank you, Wilson. Here's another question to CG, Dr. Pu. Do we still need dropout technique in LSTM RNN when we can generate data from the sample generator? Do we still need dropout technique in LSTM RNN when we can generate data from the sample generator?
Yeah, as I previously mentioned, I'm not a data scientist, but actually in our study we used the dropout layer, to utilize the LSTM. Yeah, I'm not quite sure if it can be, can be deleted or removed from our, the model. But yeah, maybe we can have a try, because recently I have seen some new actually techniques which is without this dropout layer. So yeah, for actually for further answer, probably I can direct this question to the data scientists in our team and to answer, to give a a better answer. Yeah, that's it. Yeah, thank you.
Thank you, Dr. Pu. The other question is to Dr. Pu as well. When employing model-based and data-driven approach in predictive maintenance, what are the major factors that would influence the prediction performance?
Yeah, I think this is a very good question. So we adopt a fusion methodology, which means we combine the physical failure model as well as the data-driven. So I think for the data-driven method, actually, no matter what kind of technique you use, I think the key factor is the data. Actually, if the data is accurate or not. So that's why actually we actually more rely on the sample generator as well as the limited field data. So that is why when we determine the failure parameter, we need to strictly follow the physical failure or degradation mechanism, and to determine the failure parameters of the sample generator. So actually, when we establish the sample generator, actually we actually study the failure parameter of the 4 proposed probability model very carefully, and we select the right parameters so that we can have a better data quality from the sample generator, which feed into our the predictor for the maintenance time prediction. Yeah, I think that's the key steps in our prediction. Yeah, thank you.
Yeah, thank you very much indeed. Due to time limitation, I think I will also end the second part of the Q&A session. And thank you all again for our guest speakers today for sharing their specialized know-how on the system reliability and maintenance. So may I also, ladies and gentlemen, may I at this moment, we are very honored to invite Professor Winkle Yung, the Center Director of CARES, to give us a closing remark of this webinar. Professor Yung, please.
Thank you, Dennis. First of all, I would like to extend my heartily thanks to our speakers this morning, namely Dr. Dax, Dr. Azarian, if they are still online, and also Engineer Kwok and Dr. Pu. At closing, I would like to highlight some of the things that we learned this morning. our first two speakers share with us the importance of reliability prediction and predictive maintenance. And we all understand that to make it work for reliability prediction, we need a lot of things like available information, including user conditions and environmental conditions. Somehow in the past, those are factors that we are not focusing on. But to make reliability prediction working, we need that now. Add on to that, we need data, largely from the industry, and also data from laboratory test data, audits. We also need knowledge domain for each different industries, right? So all added together with reliability modeling, we hope to help the industry to assess and predict the reliability and safety levels of their products, components, and systems. When we talk about predictive maintenance, that brings us a lot of good benefits, including cutting the life cycle cost. And in the past, we have been doing a lot of CBM, condition monitor maintenance. That is good, but not good enough, because not everything performs the same, even the same type of components or systems, because they are under different operating conditions, under different influences, from different environmental conditions, even user conditions. So we need to leverage on the newest technology, particularly POF, physical failures methodology, and DDM, data-driven methodologies, enable us to do predictive maintenance. And I'm glad in this morning that some of the biggest enterprises, including Hong Kong Electric, from what I learned from Engineering Corp, that they are spending efforts to adopt AI methodology to improve their system reliability and safety level from 4 nines to 5 nines to 6 nines, and there will be one day that we have 7 nines, right? So those are the things happening, and we have to adopt the latest technology to help our local industry and enterprises. So back in here in CARES, we're here to apply these technologies in different industries, including public utilities like Hong Kong Electric, electronics industry, transportation, components, products, and even systems in Hong Kong. At the end of the day, we hope to make a name for Hong Kong, meaning that for those designed it, manufactured it, or commissioned it in Hong Kong, no matter its components, products, or systems, they are with a very high reliability and safety level. Now in CARES, we have a blending of different expertise from different knowledge domain, including professors from electrical engineering like Dr. Boo, and electronics engineering, industrial engineering, mechanical engineering, computing, data science, audits. So with this consortium of expertise, plus we have many testing equipment, some of them are very unique in Hong Kong, we're also having a very good supercomputer to work with us. So with expertise, with equipment, we also have partnership from the industries. So they are sharing with us some of the industry data that they have, and with AI methodology and machine learning algorithm, we hope we can contribute to the smart city building of Hong Kong. So at the moment, we are pleased to share with the audience that we have already 20 partners from the industry collaborating with us so that we can collaboratively work together to contribute to their system and product safety and availability. Apart from webinars this morning, we also have regular newsletters, and upcoming we will have a whole day technical seminar, as well as another event, what we call international conference. They are all there to share with the audience what we are doing in applied research and basic research in reliability and safety, utilizing AI technology and machine learning algorithm. So without further ado, I would like to say thank you again to not only the speakers, also for the audience who is spending time this morning with us, almost over 2 hours. So thank you for your attendance. We'll see you soon in the next webinars and technical seminar and even international conference. Good day.
Right. Thank you, Professor Yung. Thank you again on behalf of CARES. I also thank you for all the participants today, our speakers, our helpers, our technical supporting companies to help us to make this webinar successful. I hope all of you will find this webinar very informative, useful, and benefits to what you are doing. Thank you. Have a nice day. Bye-bye.